Divya Prakash, I see you are there. Can you hear my voice?
Yes, sir. I'm able to hear.
My voice is clear?
Yes, sir.
Okay, and do you see my screen? Like I am displaying this PDF file,
Yes,
handwritten.
it's yeah. I can
Okay,
see it. It's visible.
okay, good. All right, so we will get started. So last class I was talking about the idea of dyads, which is a dyad is a combination of two unit vectors standing next to each other and doing nothing. No dot product, no cross product. So in this way, using E1, E2, E3, which you may recall are the mutually perpendicular unit vectors of our Cartesian coordinate system, which is in the background. So using E1, E2, E3, we can create 9 such dyads, two unit vectors standing next to each other. And clearly, when I say 9, it means I am making a distinction between E1, E2 and E2, E1. So if E1 is on left and E2 on right, that is different from E2 being on left and E1 being on right. So order matters. So in this way, we have these 9 dyads, which will be the members of the basis using which I will write a second order tensor in this Cartesian coordinate system as what I have shown here. So you see every term here has a scalar coefficient, T11, T12, and so on. And we are having two indices, unlike vectors where we had only T1, E1, T2, E2, T3, E3, we have two indices, T11, 1, 2, and so on. And they are there because they are associated with the dyads, corresponding dyads. So dyads have two indices, E1, E2, E2, E3, and so on. So scalars, the coefficients also have two coefficients. So overall, there are 9 terms that are being used to express this tensor. As I said, E1, E2 is not equal to E2, E1. And in words, when we use make a sentence out of it, T12 is the scalar component of tensor T along the dyad E1, E2. Similarly, T21 is the scalar component of tensor T along the dyad E2, E1. All right. In general, T12 and T21 will T13, T31, T23, T32 it should be, they are different in general, but there are some special tensors for which these will be equal, but that is a special case. In general, these are different. Now the sigma notation that we have been using, we can apply that here, and instead of every time writing these 9 terms explicitly on the right hand side, we can convey the same amount of information by using 2 sigma symbols. And this is how I will express the tensor Tij, Eij, 2 summations I and j going from 1 to 3. We can call Ei, Ej as the ijth dyad, and Tij can be called the ijth component of the tensor. I already said that before. Now, for example, if I am talking about T12, I will say T12 is 1, 2th component. Now it may sound a little weird. Like earlier we are familiar with saying like it's the first component or the second component. But since second order tensor comes with 9 components, and the way we have put 2 indices on every scalar component, to me it appears there is no choice but to make this weird sound that it is 1 2th component or 2 3rd component and so on. This is how we will refer to these components. We can refer to, you don't have to use precisely these words, but if you have to use a language like this, 1 2th you will have to use. Okay. Now, mind you that, so pay attention to the indices here. If you are writing TS, Tij, Ei, Ej, perfectly fine. This is how I wrote earlier. But you cannot write this tensor as Tji, Ei, Ej. So mind you, the order of the indices with the component, the scalar component, should always match the order in which the indices are appearing in the dyad. So this is the wrong representation. Tensor T cannot be written as Tji, Ei, Similarly, tensor T cannot be written as summation, 2 summations Tij, Ej, Ei. So here Ij, here Ji violated, Ji, Ij violated. So both these are wrong representations of a second order tensor. But you can, if you are willing to change both order of both the order of indices of both T and the dyads, then you will be fine. So Tij, Eij is perfectly the same quantity as Tji, Ej, Ei, right? Because the summation is over both J and I, and the order here and order here are same. This also represents the same tensor. So both these are correct representations. These are wrong representations. So later, if you are doing some algebraic manipulations, and if you start with tensor T as this, you are bound to go wrong. You will have some problem somewhere. So it's very important to start right. Either use this or this. Okay. All right. I hope you have followed this. Now I have a couple of announcements to make. I deliberately waited because some students joined late. I don't know how many of you have joined now. 82. Okay. Audit pass requirements have been relaxed. So you refer to the course document This is what I will upload today. You may recall that in the last class I said that a student must have at least 30 out of 100, and out of which 10 marks must be from the major exam. That's what I announced in the last class. But actually on Thursday, we received an advisory from the Dean's office, Dean Academic Office, and they want all courses to have a consistent policy. And thus, I am withdrawing this condition. So as long as you have 30, you can, and you apply for an audit, you will get a pass on that. You will get an audit pass, irrespective of whether those 30 marks come from minor quizzes or major. I will not pay attention to that. Okay, I hope this is clear. So this is the policy we will follow. The other policy of grading is the same. Okay. If you have any questions, please write messages in the chat box. This is how we are going to interact. Okay. The second announcement is that maybe this evening or by tomorrow, I am going to upload tutorial set 1, which will have 4 or 5 practice problems based on the concepts that we are covering on tensors. And my plan is that we will discuss this, your questions or your doubts or whatever help you need solving those tutorial set problems on Wednesday 2 to 3 p.m. And as I said before, that I expect you to make attempts solving those problems before coming to the tutorial, rather than expecting me to solve everything from start to beginning. I will not do that. Okay. Okay. So continuing with second order tensor, the next pertinent question to ask is, what is the transformation rule for second order tensor? Again, you may recall that this is part of the definition of a tensor, that the tensor should remain invariant to the coordinate system of our choice. So if I take the red coordinate system or the green coordinate system, the components of the tensor will change, but I want the tensor to be the same. It means that the components of the tensor in the green coordinate system and those in the red coordinate system should be tied by some rule. There should be some relationship. And in the last class, I derived a relationship for first order tensor or vectors. Using similar ideas, now we can derive the transformation rule for a second order tensor as well. So I have two coordinate systems denoted by like this, one green and one red. In the red coordinate system, I have, this is the representation of the tensor, no primes here. And in the green coordinate system, I have primes. Okay. Same questions, are they related? Yes, by the transformation rule of tensor 2, tensor of order 2, we can derive it as follows. The approach is similar to what we had for vectors, but of course details are different. So I start in the green coordinate system. This will be my representation of the tensor T. And then recall that the unit vectors in the prime coordinate system or the green coordinate system, I can write as in terms of the unit vectors of the red coordinate system using these numbers aij's or aip as it appears here. Okay, so ei prime, so my idea is to replace these this ei prime in terms of e1 e2 e3 and also replace ej prime in terms of e1 e2 e3. So for that I am writing ei prime as this, which comes from the definition of aij's, and ej prime can be written in this manner. So you can refer to our last lecture. There I started with the full expression, and here I'm starting with the sigma notation. I don't want to keep writing full expression every time. I hope the idea is clear by now. If not, you go back, read the material there, and then you will see how I am able to write ei prime and ej prime in this manner. So here the summation is over P, and here the summation is over Q. This J corresponds to our query of EJ prime, and this I corresponds to my query of EI prime. And P and Q are like running variables required for summation. So I am going to replace EI prime and EJ prime using these quantities here. Now, here, I want you to pay attention to the fact that this summation so in this expression, there are two summations already. One is running over I and the other is running over J. Now I'm going to bring in one more summation for EI prime and another one for EJ prime. Now mind you that whenever you are going to bring a new summation in your expression, in your primary or parent expression, mind you, the running variables should be different from the running variables which are already there in that expression. What I mean to say, this has running variables I and J, two summations are already there. Now, if you write EI prime as AII, EI, summation going from I to I1 to 3, and you put it back here, everything will become confusing. Not only confusing, it will actually be ambiguous. It will become ambiguous, confusing, and you are bound to go wrong. So every time you bring in a new summation in an existing expression, make sure the running variable is different from the ones that have already been used in the expression. So I'm using here P, which is different from I and J, and I'm using here Q, which is different from I and J and P also. Okay, I hope this part is clear. And you have to be careful about it all the time. So in this way, I have implanted two more summations in this expression. All right. This is what I wrote here, that once I and J have been used, do not use I and J as any more running variables anymore. You should use new variables. Okay. So this is what the expression of T becomes. So I have now four summations going over I, J, P, and Q. And then mind you, there are no prime unit vectors. That was the idea. I wanted to get rid of them. You can rearrange this as what I've shown here. Keep EPQ outside, and then inside you have Tij prime AIP AJQ. Okay. Now, since there is EPEQ here, I'm going to change the order of these summations, and it doesn't matter. It's just a convenience of writing and kind of identifying some patterns. So P and Q summation I'm taking out. So this corresponds to EPEQ here, and then whatever is left is this two summations running over I and J and Tij prime AIP AGQ. Okay, but recall that in the original red coordinate system, if I have to write it T in the original red coordinate system, I would be writing it like this with EPEQ and just TPQ here. TPQ will be the PQth component, right? Summation over P and Q. I can write this in terms of I and J also here, but I am trying to relate this expression to this expression. And since this has EPEQ, I have deliberately chosen to write T in this original red coordinate system as summation over PQ. So it helps me in the way that now if you compare plus and two pluses, and if they have to represent the same tensor T, second order tensor T, then it is clear that there should be this. If you match 2 plus and single plus, then you can extract 9 scalar equations. You can get 9 scalar equations, and those 9 scalar equations are, you take TPQ from here, put it on left hand side, and that must be equal to the green underline item what is here if they are to represent the same tensor, right? So this is what the expression becomes. TPQ is summation over I and J, Tij prime AIP AJQ. Okay, and indeed this is the transformation rule for a second order tensor. If Tij and TPQ, Tij prime and TPQ follow these relationships, there are 9 relationships, then you do ensure that in the green coordinate system and in the red coordinate system, the tensor remains invariant. The full tensor remains invariant. All right. Okay, I will come to the chat box in a little while. So if you have any questions, keep putting them there. I'll come back after covering the next slide. Okay, higher order tensors. We can now extend this idea for any higher order tensor. For a tensor of order 3, we know that if I tell you I'm giving you a tensor of order 3, then you know that in a 3-dimensional space, it will have 27 components going by this m raised to the power n relationship, which means that to write the full expression of this tensor, we need a 27-membered basis, which has to be formed using individual unit vectors E1, E2, and E3. And how do we do this? Now, having seen what we did for the second order tensor, you can easily extrapolate that idea and suggest that these are the 27 members which will form the basis for the third order tensor. So now you have not two members, not two unit vectors standing next to each other. Now you have made combinations with 3 unit vectors. 3 unit vectors. And as before, the order matters. Okay, so E1, E1, E2 is not the same as E1, E2, E1. So you do make a distinction between because of this order, and thus you will end up having you do end up having 27 members. Now, these you can call as third order dyads. I mean, we do not have any special word for the combination with 3 unit vectors, or for that matter 4 and 5, as it will keep increasing. So I find it convenient to call them third order dyad. Third order dyad means it is a combination of 3 unit vectors standing next to each other, and order matters. All right, so if T is a third order tensor in our course same coordinate system, the full expression will be, now T will take 3 indices, obviously, because there are 27 components, so it will take 3 indices, and those indices should match the indices of the third order dyad, and strictly following that order. So T112 is the scalar component of the tensor along the third order dyad 1, 1, 2. Okay, not 1 to 1. For 1 to 1, we have something else hidden here. It will be T1 to 1, and so on. Again, most of the times I don't want to write all these 27 expressions or even these dotted things. You just use sigma notation, and the expression will be Tijk, 3 summations, summations with I and j and k running from 1 to 3. And then again, the order matters here, Ei, Ej, Ek. You cannot write T tensor as Tijk, Ei, Ek, Ej. That will be a wrong expression. The order has to be the same what you see here. Order of this indices should be the same as the order of indices here. All right. So if I now ask a question, how do you express a 5th order tensor? T is a 5th order tensor. There will be 5 summations here, I, j, k, p, q, T, I, j, k, p, q, and then there will be a 5th order dyad, Ei, Ej, Ek, Ep, Eq, and so on. Okay. Let me go back here. Any questions? Okay, no questions. I hope I am audible. I'll just make sure again. Divya Prakash or Yash, you can hear me, right?
Yes, sir. I can hear you.
Good. Okay, good. All right. Now moving on. So this I mentioned earlier also that in my course, I will use an underbar to denote all tensors of order greater than or equal to 1. Starting from vector to all other tensors, I will just use an underbar. And so if I just give you this symbol T bar, T underbar, you cannot infer the order of the tensor unless I tell you what the order is. Okay, or if there is some other information available. However, if the expression for the tensor is given in any coordinate system, then you don't have to depend on me for that information, that what order tensor is, what the tensor order is, right? Why I'm saying that? Because you see, if I tell you T equals TIEI, you will see, oh, there is the basis member is just one single unit vector. Okay, and then of course this index is also there is only one index, so clearly this is of order 1. Similarly, if I give you this expression, what you will see is that it has a dyad or a second order dyad, right? And of course there are 2 indices, they must be there. So based on this, you can immediately say, yeah, it is a second order tensor, and so on. If I give you this expression, you will see this is a third order dyad sitting there, and thus it must be a third order tensor. So this is the sure short way of inferring the correct order of the tensor if this expression is available in a coordinate system, in your working coordinate system. Look at the order of the dyad. That is enough. I don't even worry about an ijk and a mij. The order of the dyad you look at, and that should, based on this, you can conclude correctly that the tensor is of third order or second order and so on. Okay. So now, having learned how to express tensor in our coordinate system, now let's talk about some operations. Now let the 2 tensors interact with each other and see what results after that interaction. Again, in context of vectors, you are aware of such kind of operations, like 2 vectors can dot with each other, and when they dot, what it becomes a scalar. So 2 vectors, when they dot with each other, they reduce their order, they become scalar. Similarly, we are aware of another operation called cross product of vectors, and we know that when 2 vectors cross with each other, it is a vector. So it is order is maintained to be the same. So similarly, let's see if we just open it up now, if we open up the possibilities of having tensor of any order, what are the interesting operations that are there? And again, I call them interesting because not because we just want to create these operations for fun. The fact is that when you start dealing with some physics, we try to write equations governing those physics, whether it's fluid mechanics or solid mechanics, you start seeing such expressions in which it seems that tensors are operating on each other. And that is the real motivation to learn about these tensors. For example, what I'm trying to say is that work done is rate of work done is force vector dotted with velocity. So that is coming from physics, but the expression that is there, that you can think of this as, that motivates us to define an operation where 2 vectors are dotting with each other. All right. So we will see these later. I mean, we will see enough examples, which I hope later will give you a clear motivation why we are talking about these things right now. So dot product between 2 tensors. So let's take 2 tensors T and N, and let the order be little t and little n correspondingly. 2 types of dot products are possible. Okay, in general, you can either do T dot N, where T is coming from the left hand side and N is coming on the right from the right hand side, or you can talk about the other possibility when the approach to do dot product reverses, N coming from left and T coming from right. Okay. Now, so far you have dealt only with vectors in which the order is 1, and there it doesn't matter actually. A dot B is B dot A, we know that. But as that happens only when both the tensors are vectors. If T or N, if either T or N or both are greater than or equal to 2, then T dot N is not the same as N dot T. All right, and I will illustrate this. But one thing we can infer right now is, or one thing we can conjecture right now is t dot n, or whether it is t dot n or n dot t, we expect it to result in another tensor of order what? T plus n minus 2, t plus n minus 2. And why I am saying that? Because in this dot product, unit vectors are going to get sacrificed. Just like in vectors, unit vectors get sacrificed. What I mean to say that unit vectors disappear after dot product. So if I am doing t dot n or n dot t, the initial order will be of the tensor will be t plus n. I mean initially the order will order of t is there for little t is there for big T, and little n is there for big N, the tensor, and whatever the resulting order will be the sum of these minus 2, and those two represent the sacrifice tensors, one from each side. It will become more clear with this example. This formula or this conjecture that I am making, it is actually consistent for vectors. So if both are vectors, t is 1, n is 1, so and then minus 2, it means that the resulting tensor is going to become a scalar. That's what happens. Okay. I'm going to take an example, now a concrete example, t equals 2 and n equals 1. And let's find the expression for t dot n in our Cartesian coordinate system. So t dot n I can write as this. So I'm writing the full expression for t here, okay, using I and j as indices, and I'm writing n using p as index. Again, I'm following that rule. I am going to get 3 summations, so I am preparing myself that the running variable of a summation should not be interfering with the running variable of another summation. So you have to be careful about it. So EI, EJ here because second order tensor, and NPEP because it's a first order tensor. So this thing has 9 terms dotted with NPEP. Now here I am blowing up and blowing the expression up, and I'm showing T11 E1 E1. So I take this, only this term here, and I okay, now I'm trying to show all the 9 terms. So T1 1 E1 E1 dotting with NPEP, T1 2 E1 E2 dotting with NPEP, and so on. So in this way there are 9 groups of terms that will be here. Now let's focus on the first term alone. Okay, so that will be T11 E1 E1, and then I am expanding it. It is N1 E1, N2 E2, and N3 E3, right? So this is what I get. I will get 3 terms. This dotted with this dotted with this, and this dotted with this. So I have all these 3 terms written here. Now, what is the rule of dot product? The rule of the dot product is for higher order tensors that the closest unit vectors are supposed to dot with each other. So here E1 is supposed to dot. This is the rule we are making. E1 has to dot with E1 here. Here E1, this E1 has to dot with E2, and here this E1 has to dot with E3. Okay, this is the rule of dot product for higher order tensors. Now you'll see that since our coordinate system has orthogonal unit vectors E1 and E2, E1 dot E2 will be 0 and E1 dot E3 will be 0. So we will have only one term surviving out of these 3, and that will be T11 E1 N1. And these 2 unit vectors will be sacrificed. They will just become 1. Okay, so this dotting with this gives me only one term, which is T11 N1 E1. Now, similarly, you can go back here and work on each one of these. Now, T12 E1 E2 and PEP when dots, you can show that. Well, first you expand. This is the full expansion. I have tried to be as elaborate as possible at this stage. So I have expanded it T1 1 T1 2 E1 E2 everywhere, and then NPEP I have expanded as N1 E1 N2 E2 and N3 E3. Again, a similar thing will happen. 2 of these terms will go to 0 because of the closest unit vectors dotting with each other, and one will survive, and that survivor will be T1 2 E1 and 2. Okay. By this time you can start recognizing the pattern. Actually, there is a pattern. What is the pattern? So this unit vector is supposed to dot. So T11 this unit vector is E1, so N1 is retained here and E1 is retained. This E1 retained is from this side, from here. Here what will be retained is E1 will be retained, and this unit vector will dot, so it means N2 will come. I don't know how clear I am, because I don't know how effective this cursor moves on your side, but I'm sure if you observe it closely, you will see there is a pattern, and based on that pattern, you really don't have to keep expanding it every time. Recognizing that pattern, you can actually write that T dot N for this example will give these terms. Okay, these 9 contributions will come, and these 9 contributions are coming from these 9 expansions. Okay, which again you can recognize the pattern and write it in compact form, and that compact form is Tij Nj Ei. So based on observation, you can write it like that. Okay, so this is the dot product of two tensor, and then you recognize that what is the order of this tensor. The order of this tensor is 1, and which is in this case T was 3 and was sorry, T was 2 and was 1, so 2 plus 1 3 minus 2 1. So T plus N minus 2 is right. It was a right guess. And again, I'm saying it is I'm sure it is a first order tensor because there is only one unit vector here. Okay, so this is the expression for T dot N. Let's flip the order of the two tensors and take N dot T. Okay, I'm not writing all the steps here, but if you do, if you follow the steps, or if you can recognize the pattern and write it directly, it's very nice. It turns out that N dot T is this, which again is a first order tensor, but there are differences. It has Nj Tji, okay, whereas it had Nj Tij. So they are not the same. I've written a few more things here to make this more clear. Yeah, how do I infer that T dot N and N dot T are not same? This is how it is. You look at the indices here, but while looking at the indices, you have to make sure that before making a direct comparison here, you have to make sure that both expressions have EI. Both expressions have EI. Both expressions with summation signs are EI. Otherwise, you may go wrong. So let me illustrate it here, what I'm trying to say. So see, in this expression in T dot N, if I ask the question, what is the ith component of Tn? How do I identify the ith? So this is the full tensor with summation sign. If I just ask you to give me the ith component of Tn, and mind you, the ith component will be just a scalar. So ith component is coefficient of Ei in the full expression, right? Coefficient of Ei in the full expression. Now, if you try to identify coefficient of Ei, of course it is, you remove the summation with I, and whatever is left is the ith component, Tij, Nj, J going from 1 to 3. This is the ith component of the tensor. Now, to ascertain T dot N is not equal to N dot T, find coefficient of Ei from Tn. I'm giving you a general rule, which you can use for any order tensor. Find coefficient of Ei. Well, any order tensor, you'll have to change the indices, I mean the dyads here also. In this case, find coefficient of Ei from Tn and coefficient of Ei from Nt. And if they are not identical, then you conclude that Tn is not equal to Nt. So we found that here T dot N was this expression. And as I asked this question before, what is the coefficient of Ei? You can easily identify that as Tij Nj summation over J. Now, one thing I want to highlight here, sometimes students make a mistake here. See, Tij Nj summation J1 to 3 is just a scalar, right? It's just a scalar. Now, I can write Tij Nj summation J1 to 3 as also Nj Tij. I mean, whether Tij appears before or Nj appears before, it doesn't matter, right? So these two remain the same. So this order is not going to matter. Now, coming back, now we find N dot T. Okay, so if you find out, if you find n dot t and it turns out that this is the expression you get. Now, if I ask you based on this expression, what is the coefficient of EI? It is not very obvious because there is no EI here, right? But that is not a problem. You can do, you can follow a step and then it will become very clear what is the coefficient of EI. What step we have to do? So here EI is not visible, but we can change I and j because summations are over both I and j. So I and j are running from 1 to 3. So I can interchange I and j consistently. All i's if you change to j and all j you change to I in an expression like this, the overall expression, the overall quantity should not change. So if you have n dot t with ej here, and if you change I to j, j to I everywhere, it becomes nj tji ei. That's what I wrote here. That's what I wrote here. Okay, so now if I ask you the question, what is the coefficient of ei in nt? Is now very clear because ei is there. All right, so now you can identify that as nj tji. All right, I hope you have followed this or followed what I said. Now earlier I said that you can extend this idea for higher order tensor. Now if you extend the higher order tensor, suppose you have to see whether two tensors of second order are equal or not, then what you will seek, from one side you will seek the coefficient of ei ej, and from the other also from the other expression also you will seek coefficient of ei ej. If ei ej is not there, if it is ep eq, then you can change p to I, all p's to I and all q's to j, and then you will have ei ej sitting there, and you can isolate or extract out the expression, the coefficient of ei ej from the second tensor also, and then you can compare whether they are same or not. So in this case, n dot t resulted into nj tij, and sorry, t dot n resulted into nj tij, and n dot t resulted into nj tji. So mind you, they are different. Again, you need to pay attention here. Nj is fine, but there is a tij and there it is tji, and thus I am saying they are not the same in general. But so far I have not put any condition on t. So Tij is in general different from Tji, and that's why I conclude that in general n dot t is not the same as t dot n. Okay, so two things we learned: how to do dot product with higher order tensors, and also we recognized the order in which the tensors participate in the dot product. That changes the quantity, except the case when both are vectors. There the order doesn't matter, but for anything else, the order does matter, and you have to be careful about that. Okay. Double dot between two tensors. Let me go back. Any questions? Example of a third order tensor. Example of a third order tensor. Okay, we will see in fluid dynamics that when you have turbulent flow field, uh, there is a type of stress that is generated because of fluctuations in a turbulent flow field. That stress is a second order, and then that stress is transported by another velocity component. So that expression which represents transport of tensor by a velocity vector, you will see that that becomes a third order tensor. You must not have seen this, you must not have come across this, but wait for some time and you will see. Besides that, I cannot think of an example with which you can readily relate right now. Okay. Don't we use 2 underbars for second order tensor, 3 for third, and so on? Maybe some texts do use that, but I don't find it necessary, because as I said in context, so first of all, I should say there is no universal rule. It's not cast in stone that everybody in the world should follow that. It is contextual. Some textbooks are written where the authors say that they will use this notation and they should stick to that so that the communication is all right. So it is a matter of choice. I will use just an underbar, and as I have assured you that you would know from context what order tensor is. But then I must tell you, Aditya, if you are dealing with 10 order tensor, are you ready to put 10 bars below every quantity? In fact, even though you are saying that for third order tensor, they put 3 underbars, I have not come across any text which cares to put 3 underbars. But I'm not claiming that it may not be there. You might have seen it, but I find already unusual putting 3 bars under every quantity. Not only it is tedious, it will create a lot of issue if you are writing on Word or even some other word processor. So no hard and fast rule, no hard feelings about it. We have to just make sure we have what we want to have in our case, and we have to be consistent. What is the physical meaning of dot product of tensor? Again, the same question. I don't, well, physical meaning of dot product of tensor in general, I don't know. As I said before, you give me a quantity and then you can have a physical meaning. Dot product of force and velocity has a particular physical meaning. Dot product of some other quantity with some other quantity can have a particular physical meaning depending on the branch of science or the physics that you are studying. I cannot think of a general physical meaning of dot product. I don't know. Whatever I have read, I have not come across, and that doesn't worry me. Even when I say I don't know, that doesn't worry me, because these are mathematical tools. Actually, when you come across physics, then you ask these questions, and it's good to get answers. But right now, it's a mathematical framework we are building. We don't have to interpret everything physically right now. TIJKL, TIJKI, implies that. Okay, I need to look at this. TIJKL. What do you mean by 3 dots here? So what order tensor we are talking about? TIJKL. And in 1 and t greater than 0. Okay, so Ankush, I think what you are asking, that given certain conditions on the components, and please respond with yes or no if I am understanding your question correctly. I think what you are saying is that if we know that there are some constraints on some components, like TIJKL dot 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 is equal to T dot dot at LKJI, there are already given some constraints, then can we infer whether T dot N equals N dot T or not, right? That is your question. Given the constraints, can we infer T dot N equals N dot T or not? Please write yes or no. Yes. Okay. Yes. So if those constraints are given, you can check, and yeah, it may turn out that T dot N equals N dot T for special cases. So mind you, when I said that T dot N is not equal to N dot T, I also added that statement, right, in general. But yes, if you are given some further conditions, then you can have T dot N equals N dot T even for tensors of higher order. I'm not ruling out that possibility right now. Okay, I hope I have answered your question. All right. Okay, let me go back here. So double dot, I will try to increase the speed a little bit because I want to complete a certain part to prepare ourselves for tutorial. And I think it will not be too much of injustice because all these notes are there. Even if I go a little fast, if you do not understand everything, you read the notes. And if you have a question, you can always come back, especially in the tutorial. Since the reference material is with you, I can go a little bit fast. Now, I'm reminded I should tell you one thing, that in my course, if you want to do well, if you want to be able to answer the questions, the kind of questions I ask in quizzes and exams, one thing you have to make sure that, of course, you attend my lectures, attend my lectures or watch the recording of the lecture, but then also read the notes and derive things on your own, like many things I'm showing here, right? Like this kind of expression I will show a couple of steps, not all of them. I really expect the students to complete those steps and make sure that they can handle it on their own. I mean, just reading the lecture notes and just listening to me will not be enough if you want to do well on my course. You will have to do things on your own. Whatever I show you, you have to do it using your own pen and paper. Only then you will get to the level of understanding based on which I ask questions. So this course is very different from engineering mechanics, where I know students hardly read notes. In fact, I know that when I was teaching the course recently, I know that when I derive, students feel why I am wasting time deriving. I should give them more examples to solve. As students have told me, see, in that course, I can still understand that part because there is less concept and there are a lot of practice problems, in the sense there are many solvable problems which you can solve and kind of exercise your do exercise of the concept. Here in this course, unfortunately, you will not have too many solvable problems. I cannot keep giving you books, references of books in which you will have hundreds of problems and you can practice and master the concept. No, there are not many solvable problems. So here, the idea is you learn some concepts and hopefully you will be able to solve some unsolvable problems, either by using CFD or by doing some experiments and getting some insight of it. So what I'm trying to say, it is a concept intensive course. It's not a practice. It's not a course which is based on practicing problem solving. So don't expect me to give you too many questions for practice because I don't have. And the second is you have to derive things on your own. You have to get that understanding to a level where you can, I ask you to derive something and you should be able to do that. So that is important for you to do well on this course. There is no escape from this. Double dot between two tensors. Now for double dot to be sensible, both t, small t and small n, which are the orders of the two respective tensors, t and n, they must be greater than or equal to 2. Then only it will make sense, then only it is defined. Okay. The order of the resulting tensor, you can conjecture that it would be t plus n minus 4. Why I'm saying -4? Because two tensors from either sides, from t and n, will be sacrificed doing those two dot products. So we expect the order to be t plus n minus 4. Illustration with an example, let t equals 2 and n equals 2. You have t double dot n. I'm writing t as summations over I and j, and n summation over p and q. And again, the same thing, ij taken, never repeat ij again. Take new indices for summation, otherwise it will become a mess. All right, for illustration purpose here, I'm writing this expression fully, the 9 terms here, and then I'm showing this has to dot with NPQ, EP, EQ. It means that each one of these from the left side should go and to do double dot product with the whole 9 terms that are sitting here. So a lot of terms are there. For illustration, I focus only on T11, E1, E1, double dotting with NPQ, EP, EQ, the full tensor. Okay, this is what I'm doing here. So now I am writing NPQ also in the full as sum of full 9 terms. And then what is the rule for the second order tensor? Rule of double dot product. What is the rule for double dot product of tensors? Rule of double dot product is first the two closest unit vectors will dot. So the first dot product will be the closest unit vectors, the one coming from left and the one coming from right, which are the closest neighbors, they will dot. And once they have dotted and sacrificed themselves, then the two nearest neighbors will again dot. All right, this is the rule of second to double dot. So see what is happening here. I'm sure I've tried to show things with arrows here. So first dot product will be here between E1 coming from left side. I hope you are seeing my cursor, and then this E1. Once they have dotted, then the remaining one from the left and the remaining one from the right, and which are closest to each other, will dot again. All right, so this particular term will have even as first dot product, which is 1, so it survives, and then even and even dotting again, so overall it is going to survive. But other terms are not that lucky, in the sense that you see that the first dot product of even and even in the second term will indeed survive, that will be 1. But then what we will be left with is even coming from left side and E2 coming from right side. And clearly when even dot E2 happens, that is going to be 0, right? So if you apply this understanding for all the terms here, what I have written, the 9 terms, you will see that only one survivor comes out of this whole thing, and that is T11 and 11. The rest of them are all gone after consequent to two dot products. Okay, it is 9:50. I'll take 4-5 minutes more and then I will wait for your questions. So let me continue with this. Okay, let me ask this question. Am I right that you have another class at 10? Somebody please write yes or no. Or you guys are free on You have, okay. So I will, yes, I got the answer. Okay, so I will finish in 3-4 minutes, and then make sure that you are free to go to the other class. Okay, so rule out, so as I said, this one gives me one term, and similarly, so this is an example. You say, I'm saying similarly, and I'm writing all the survivors of the remaining dot products, double dot products that will happen here. So I explained one, and then I am writing directly the remaining one. And this is where your contribution, or rather your participation, comes. When you are going to read the notes, you read the notes and you don't stop there. You go and just make sure that you get all the other terms, either by pattern matching, that is acceptable, or if you are not able to recognize the pattern there, you don't shy away, or don't be lazy. Go ahead and expand things, because that will enhance your understanding. Okay, so consequently, we have all these terms coming from 9 terms which we had earlier, and then you can write them in index form, in a compact form, as Tij and Ji. So T double dot n, when both are second order tensor, gives you Tij and Ji. Now, if I ask you a question, what is the order of the tensor? How will you infer looking at this? There are no unit vectors standing here, no unit vectors, no dyads of higher order. So clearly it is a scalar. All right, clearly it is a scalar. Is this formula or the conjecture that I made, T plus n minus 4, correct? So T was 2, n was 2, and then I said the resulting tensor after double dot product will be T plus n minus 4. So 2 plus 2 minus 4, indeed the tensor has 0 order. Okay, so double dot product results into tensor of order T plus n minus 4. Okay, so here one thing you have to be careful, nearest unit vector should dot, and if you follow that, you will get the right expression. Some more definitions. Transpose of a second order tensor, it is also second order tensor M. So transpose of a second order tensor M, it is symbolically written as MT. T means transpose. So if M is written as Mij Eij, it must be written as Mij Eij in our coordinate system. What is the difference between M and M transpose? You observe the difference is you keep the unit dyad indices of the same order as before, as M, and you change the order of indices in M. So that represents transpose. And transpose is not necessarily the same as M. Again, there may be some conditions in which M and M transpose are same, but in general, they are not same. So Mji, Ei, Ej is not the same as this. Nevertheless, this is the definition of the transpose of M. Now, interestingly, you can write the transpose also as Mij, Ej, Ei. So you either change the order of the dyads or the indices of the dyad, or you change the order of the indices in the scalar component. They are both legitimate representations of the transpose of M tensor. As I said, M and MT are two different tensors. However, for some tensors, M and MT are same. Then M is called a symmetric tensor. And mind you, I'm only talking about second order tensor right now. So if M and MT for a second order tensor are same, it's called a symmetric tensor. And in that case, you can show that Mij must be equal to Mji. M12, 21, M23, 32, and M13, M31 are same. Like stress tensor is a symmetric tensor. Inertia tensor, APL 100 was a symmetric tensor. Some second order tensors are called anti-symmetric tensor. Why? When they are called anti-symmetric tensor? When Mij equals minus Mji for all Ij, which means that, so this is the condition for a second order tensor to be called anti-symmetric. So this relationship implies M12 is equal to minus M21, M13 equals minus M31, M23 equals minus M32, and M11, M22, M33 are all 0. Okay, it's an anti-symmetric tensor. All right. I will finish with this slide. Given any tensor of order 2, again, I'm talking only about second order tensor. And again, I am kind of picking and choosing certain definitions with the motivation that we are going to encounter these in fluid mechanics. All right. So given any tensor of order 2, say A is the tensor of order 2, it can always be split into a symmetric and anti-symmetric tensor. you can split the tensor as A into a symmetric tensor and an anti-symmetric tensor. The symmetric tensor is defined as A plus A transpose by 2, and anti-symmetric is defined as A minus A transpose by 2. All right. Cross product between two vectors. Now, mind you, cross product is defined only for vectors. Cross products are not defined for tensor. If any of the tensor, participating tensor is of order greater than 1, it's not defined. It's defined only for vectors. And you are familiar with this. A cross B, in index notation, you can write them like this. Again, making sure if P is taken here, is not repeated here, Q comes, then use these relationships between the orthogonal unit vectors, and you can arrive at this expression. All right, I stop here. And again, these are the things which you should make sure you make sure you use pen and paper and get these relationship what I have shown here. So now people who want to leave may leave. Others, if you have any question, I am unmuting your mic. We can take maybe one or two questions. I will wait till 10. Akash Patel, quite similar to matrices. Yes, because as I said in the last class, matrices are actually a symbolic representation of the components of second order tensors. So actually the idea comes from here, and then it is extended to matrices. But the way the sequence in which you learn things, you have come across matrices, so you feel that it's like matrices. But point is that matrices borrow the ideas from tensors, the way I am telling you. So yeah, I mean, not a problem. If you think it is similar, yes, it is similar. Akash. Okay, I'm going to extend the class to 10 minutes. I'm just extending. You don't have to be here. I just want to make sure if somebody has a question, I address. Others free to leave, no problem. Your mic is unmute if you want to say something. From my side, it is unmuted. If you want to say something, feel free to do so. So even though I am waiting, and if nobody is asking questions, it's fine. But I think in the recording, maybe I will delete this part unnecessarily. You don't have to keep this. But I am here. Yash and Divya Prakash, you may also leave. You don't have to wait for me. In case you are still here, please feel free to leave. And thanks for joining. How does the result that dot product is of order? How does the result? I don't know, Amitesh, what you mean by how does the result? It's based on observation. I have not made any derivation. You look at the examples, the way we have defined the dot product rules, you will see that that is true. So I am not asking you. So even though I said a conjecture, it's not that you have to make that conjecture. Maybe I am able to make the conjecture because I am familiar, but there is no derivation of that. Yes, observation based, Amitesh. Yes, experience based. When you perform the operations, you end up seeing something which is always consistent with this. And then you can add sense to it that -2 because it will sacrifice 2 unit vectors, they will dot. The purpose of the rules for dot and double dot product is just to ensure that all terms are included in the final expression, right? Purpose of the rules for dot and double dot products is just to ensure that all terms are included in the final expression. I'm not able to follow your question, Parimit. You have to elaborate it. You can unmute your mic and speak. It'll be easier. Parimit, I am not able to understand your question. You have to elaborate. Purpose of the rules for dot. I don't know why you are not responding, but let me say something which may help you. The purpose of defining rules for dot and double dot product is governed by, again, the fact that when you try deriving equations for physical phenomena, so various physical phenomena, when you do get combinations of quantities which can be called, which can be represented in a compact manner using the definitions of dot and double dot product. So the definitions are governed by the kind of combinations of quantities that you encounter while deriving equations. We can keep going on defining newer and newer type of dot products if there is a need. All right. Double dot and single dot are defined because in many branches of science you come across such combinations of quantities. For some reason, I am unable to do so. I'll get back to you later, sir, after giving it a thought. Sure. Okay. No problem. You can write an email also to me, Parimit, or next sessions, especially the tutorial session. I think we will have more time. Okay, so it seems session will end soon, and it seems there are no more questions, so I will not extend the class. I will let it end on its own. I hope it ends on its own.